Hey everybody, in this lesson we're talking about Lewis structures, lesson number 12. We can draw how molecules look based on their reacting valence electrons. So that's a big idea for today. So what are Lewis dot diagrams? Well, now, we know that when we drew Bohr models, we have to draw every single electron that the atom has. But we only really care about the outermost electrons, which we call the valence electrons, because they're the one that do most of the reacting. So, only valence electrons react. Because of that, we can draw our atoms with valence electrons only. Okay, so let's go a little review about this. Let's look at sodium. Sodium has a symbol Na. Sodium belongs to the alkali metals, and the alkali metals, as we know, are all having one valence electrons. The alkaline earth metals have two. Transition metals have multiple different ways to have valence electrons, but these ones on column 13 have 3, 4 valence electrons, 5, 6, 7, and 8. So those are how we remember how many valence electrons there are per each section of the periodic table. So if you look at sodium, we will see that sodium just has one, so we could draw it like so. Magnesium is part of column number 2, so we could draw it like this. Oxygen is part of column number 16, and it has 6 valence electrons, so we go north, east, south, west, and then we pair them up. So that's what we have here in terms of the Lewis dot diagrams. Now this should still be reviewed because you actually complete this in Science 10. So what are some different ways we can always represent any chemical formula? Of course we have the formula itself. So an example is, let's say we have fluorine gas, so F2. We also have a dot diagram. And a dot diagram is where you show bonds as dots. Remember, 2 electrons is a bond. And then last but not least, we also have the structural diagram. And this is where we replace the dots with dashes to show bonds. So these are examples of what we have for representing chemical formulas. Now let's dive in right now with some Ionic Lewis structures first. Remember, ionic means to transfer electrons. So in this case, it's the same as Bohr models, which means that we still transfer electrons and show charges of ions with brackets. So let's try this out. Let's look at magnesium chloride. What the Cl2 means is that there's 2 chlorines. So first of all, let's draw magnesium. Magnesium looks like this. While chlorine, being on column 17, has 7 valence electrons. So look at this then. What does magnesium want to do? Magnesium wants to lose these 2 electrons to have a photo shell. So it's going to say, hey, take these 2 electrons away from me. Chlorine has room for 1 more each. So what's going to happen? Magnesium is going to donate its electrons to chlorine. And what you're going to get here is you get magnesium has lost all of its valence electrons, so it has a +2 charge. Chlorine, on the other hand, has gained 1 electron each, and it's going to have a minus charge for each of them. And this is what magnesium chloride looks like as a Lewis structure. Now if you count the number of valence electrons, you had 8 valence electrons before this thing combined, and you still have 8 valence electrons afterwards. So the number of electrons should always be the same. Likewise, the charges should still be neutral. This was neutral, this is still neutral. Let's look at magnesium oxide. So again, magnesium, it looks like this. Oxygen looks like this. So in this case, what's going to happen is you're going to have magnesium donating both its electrons to oxygen. And what you're going to get is you're going to get, again, magnesium looking like this with a +2 charge. Well, oxygen gained 2 electrons, so it's going to have a -2 charge. What about covalent Lewis structures? Well, let's look at simple ones first. Remember, covalent is always between two nonmetals. And in this case, it's sharing electrons. But the big thing is, still obeys octet rule. So let's look at an example for F2. For F2 here, we have fluorine. Each fluorine looks like this. And what's going to happen is, because each fluorine is pretty electronegative, they don't want to give away electrons. Instead, they're going to overlap and share these 2 electrons, and when they do that, they form a physical bond. So if I draw a physical bond here, it'll look like this. We have 2 electrons between them being shared, and still the 6 other electrons around that aren't being shared, and they're what we call the lone pair electrons. So right here, these are what we call our bonding electrons. Well, these ones are called, so I'll change the color. These ones are lone pairs. Okay. These are lone pairs, and these are bonding. Now, covalent bonds are what we call physical bonds, while ionic bonds are electrostatic because there's attraction based on opposite charges. Now if we look at, here's some other covalent bonds. Let's get O2. We will see that O2, well, oxygen looks like this. There's 2 of them. You can see this time, they're going to share 2 sets of electrons, because they need to have 2 sets of electrons being shared to be a full octet. So in this case, you're going to have oxygen with 2 sets of electrons between them, with still a set of pair of lone pairs, so 4 lone pairs around each oxygen still. Now this is starting to look a little bit tricky. So another way we could show it is what we call our structural diagram, where we show our bonds as dashes. So what's going to look like now? It's going to look like this. So now we can physically see that those are bonds, and those are 2 electrons each per dash. Last one is H2. Now H2, hydrogen, we know, only needs 2 electrons in its outermost shell. So these 2 are going to share like this. And when it does that, you're going to get hydrogen like that. And that is hydrogen gas. Now, what are some ideal bonds for nonmetals? Well, in this case, it's based on the valence of the atom. Based on valence of the atom. And what is the valence of the atom again? It's the number of unpaired electrons. So for example, hydrogen, chlorine, fluorine, bromine, iodine just needs 1 bond. Oxygen, sulfur, selenium will be 2 bonds. Nitrogen, phosphorus, arsenic will be 3 bonds, because they have 3 sets of unpaired electrons. And lastly, carbon, silicon will be 4 bonds. So these are what we call the diatomics up here, But what happens if they're not diatomic? How do we draw our Lewis diagrams for them? Well, there's a little strategy. The first couple steps is a math part where you're trying to figure out how many bonds. So you're going to find number of bonds. Okay, so this is not going to be exact science, but it's an easy way to find and expect how many bonds you have. So step 1. Count number of atoms and multiply by 8. And what it's going to tell you is the total number of electrons for octet. We're expecting to treat each element as an individual, and if each element has 8 electrons to become a full octet, we'll find that number as a total number of electrons for the octet. There's an exception though, except hydrogen needs 2. Okay, step 2. Count number of valence electrons. Total. Making this I accept hydrogen is 1. Alright. The last step to find the number of bonds is this. Subtract step 1 from step 2 to find number of electrons in bonds. Remember, 2 electrons equals 1 bond. So if you have 8 electrons, that's 4 bonds. So this is a way to find the number of bonds. But how do you draw your compound? Well, to draw your compound, to draw compound, what you want to do now is you want to, first of all, draw what we call a skeleton. A skeleton as symmetrical as possible with usually carbon in the middle. Okay, that's step 1. Step 2, fill most electronegative element with valence electron first. And now, if you used up all your valence electrons and you have no more valence electrons left, and some of the elements don't have a full octet, step 3 is where you rearrange to form multiple bonds for elements without full octets. So we're going to practice this with these next few examples. So let's take a look. Let's look at Cl2. So first of all, let's find out how many total bonds we should expect. So step 1, how many elements do you have? Well, you have carbon and 2 oxygens. That's 3 atoms. So total electrons, if you were just dealing with them individually, you have 3 atoms times 8 electrons. You should expect 24 electrons if they're individual atoms. Number 2, how many valence electrons does each one have? Well, let's take a look. Carbon has 4. Oxygen has 6, and there's 2 oxygens. So in total, we should have, as you can see, we should have 16 electrons. Step 3, find the number of bonds. 24 take away 16, that is 8 electrons in bonds, which means we should have 4 bonds. Okay, let's draw it. So first of all, we're going to make it as symmetrical as possible. So we don't want to do this. This is not symmetrical because there's no symmetry involved in this process. So instead, how can we make it symmetrical? Well, we can make it where carbon's in the middle. So if we draw carbon in the middle, now this is symmetrical Okay, so these bonds right here just used up 4 valence electrons, and we have 16 valence electrons total in this compound. So 4 of them are taken away. We still have 12 more to go. We want to fill the most electronegative element first. In this case, oxygen is actually more electronegative than carbon. So we fill oxygen with to make them each a full octet. So there's 6, and here is another 6. So in total, right here, look at this. We just used up all of our valence electrons. We have 16 valence electrons. We have 2, 4, 6, 8, 10, 12, 14, 16 valence electrons used. Oxygen has a full octet, but carbon does not. Carbon still only has 4 electrons. And that's where number 3, rearrange to form multiple bonds for elements without full octets. So in this case, what happens here is oxygen and carbon are pretty close with electronegativity. They can actually say, hey, take 2 of these electrons away and form a bond. Same with this one. Remember, symmetry is important here. So in this case, another set of oxygen will give its electrons to form a bond. And what you're going to get is you're going to get this compound to look for. So you have 2 oxygens here with a carbon with 2 bonds between them now. And we have our lone pair electron still. And that is the Lewis structure of CO2. Let's look at NH4. For NH4, let's look at the total number. So number 1, actually I'll change the font color. Number 1, the total electrons. So in this case, nitrogen is 8, hydrogen is 4. So 8 plus 4, and this should be 12 electrons. Okay. Oops, it should be 8 plus 8 because each hydrogen is 2. So it should be 16 electrons. So 8, and then it should be 16 electrons. Okay, number 2, valence electrons. Nitrogen has 5. Hydrogen has 1 each. So that means there's 4 hydrogens, that's 1 each. That means that's 9 electrons. But you gotta remember, it's ammonium. It's a positive symbol. And when it's a positive symbol, what that means is it lost electrons. So instead of it having 9 valence electrons, it actually has 8. That is no longer 9. It should be 8. So in total, if you were to subtract the 2, 16 take away 8 is equal to 8 electrons in bonds. So that's 4 bonds. We should expect 4 bonds. Okay. So if you look at this, nitrogen should be in the middle to make it symmetrical. Hydrogen surrounds it. That's our skeleton diagram. How many valence electrons do we have in total here? Well, as you see, we had 8 valence electrons. Well, each of these bonds is 8 electrons. Each of these bonds makes up 8 electrons. We have 4 bonds. This is actually our final Lewis structure. Except for because this is a positive ion, you gotta put brackets around it to show that it's the case still. So you still have to show brackets if it's an ion. So you see how this thing predicts 4 bonds? It has 4 bonds. Just like CO2 predicted 4 bonds, we have 4 bonds. If you look at CH4 now, for CH4, again, let's count the number of total electrons. Total, we should have 8 plus 8 again. It's 16 electrons. Number 2, valence electrons. We should have 4 plus 4, that's 8 electrons. So that means number 3, we should expect 16 take away 8 electrons in the bonds, which is 4 bonds. So again, symmetry, carbon in the middle, hydrogen around it. We just used up all of our 8 valence electrons, but if you look at it, hydrogen has a fuller shell, carbon has a fuller shell. This is the Lewis structure of methane gas, which is CH4. Now there are some exceptions to the rules. One of the big exceptions is what we call electron deficient molecules. Now what does this mean? Well, boron, beryllium, and aluminum have low electronegativities. And because they have low electronegativity, they cannot form full octets because their neighboring atoms do not want to share its electrons to form multiple bonds. So I'll show an example of that. We should look at our next example, which is BF3. So look at BF3 here, we could see that boron trifluoride looks like this. If we were to count, again do the math, 1 total, we should expect to have a total of, well, each one could have 8, so it's 4 times 8, that's 32 electrons total. Valence electrons. Boron should have 3. Each fluorine should have 7, so that's 3 plus 21, that's 24 electrons. That means bonds, how many bonds should we expect? We should expect 8 electrons or 4 bonds. But in this case, what's going to happen is if I finish drawing the Lewis structure of this atom, of this molecule, you're going to see that I've used up all my valence electrons right about now. So all my valence electrons are used. So if you're looking at previous questions, you might go, oh, this fluorine's going to give these 2 electrons to form a bond, so that boron has a full octet. It won't. Fluorine is very electronegative, and because of that, it doesn't like to share electrons, especially with boron. So in this case, it keeps its electron, it won't give it to boron, and boron thus doesn't have a full octet. And this is what we call electron deficient molecule. Another exception, there are elements that can have so the other exception, elements with empty d orbitals can break octet rule. And what that means, have more than 8 electrons. So these are, for example, sulfur, phosphorus can have more than 8 electrons around it. Silicon's also another one. So these are examples of ones that have more than 8 electrons because they're empty d orbitals. So if you look at this, these p orbitals, s orbitals, and d orbitals are fairly close to energy. Because these are empty, these e orbitals, these 3d orbitals, electrons go there, and thus you can have more than 8 electrons, more than 4 bonds. So if we look at PCl5, if we do the math, we will see that if we have total, our total here should be 48 electrons, because there's 6 electrons, 6 elements total, times 8, 48. Valence. Phosphorus should be 5. Each chlorine is 7. We should expect 7 times 5, which is 35 electrons from the chlorine, plus 5 from phosphorus, 40 electrons. So bonds, we should expect 8 electrons or 4 bonds. But the moment you draw this compound, you can already see that there's no way that it could ever have 4 bonds. Because right here, right now, you see that there are already 5 bonds right away. And that is actually okay, because phosphorus can have that. And if I draw the rest of the valence electrons, this is phosphorus pentachloride, because it can have more than 4 bonds, in this case, around the phosphorus. So that is okay. As always, make sure you keep yourself safe and healthy, and I'll see you soon.